Welcome, Kaylin, Kendra, Keston, Lanisha, Nigel, Monier. Welcome to our session. Now, I got a little bit of a problem. I have a student who was working and has asked me to delay turning in the assignment, the exam. So if I'm going to allow that person to turn theirs in late, I want to know if any of the others of you want a little more time as well before I grade the papers. If you want to have a little more time on the exam, just text me. I mean, just respond and mute, respond in chat. And I won't grade the papers just yet. I will give everybody else another afternoon. If you think I should go ahead and proceed, I want to do, I can, but I'm giving the class a chance to weigh in on because only one person asked for extra time, so I want to see what the others are wanting.
I was doing this. I was just in the middle of writing it. Okay, all right.
So why do I hear you all on the recording?
Ma'am?
I don't understand why you're recording.
Are you on mute?
I am.
I accidentally
Okay. Thank you for responding, Nigel. Well, right now, I think I'm going to just move ahead to chapter 5. So I sent you the PowerPoint presentation, the equation quiz, and the first assignment. So let's just start there today. Okay. So do you all see chapter 5, dynamics of uniform circular motion? Someone, yes or no? Just come off mute, yes or no?
Yes.
Okay, great. All right, so let's start a new chapter. So this chapter is a very short chapter. Hopefully we can cover it in a couple of days and you will be able to follow along. So what is the definition of uniform circular motion? Now, so far we've discussed motion in one dimension. We've discussed motion in 2 dimensions. And now we're going to discuss motion around in a circle, in this uniform circular motion. Hold 1 second. Okay, class. Uniform circular motion is the motion of an object traveling at constant speed on a circular path. Okay, so here we have a picture that's showing you that the object is moving in a circle of radius r and it has a speed. Okay, what is that speed? That speed is distance over time, but the distance that an object travels, if it makes one complete circle, is the circumference of a circle, which is 2 pi r. So my distance is 2 pi r. And now we're using uppercase T as opposed to lowercase t, because this t will be the time it takes for the object to travel once around the circle. That's called the period of revolution. So now we're using uppercase T to sort of distinguish that from just regular time. This time will always represent the motion, the time it takes to make one complete revolution. So here we have our first example. The wheel of a car has a radius of 0.29 meters and is being rotated at 830 revolutions per minute on a tire balancing machine. Determine the speed at which the outer edge of the wheel is moving. Now, before we can determine the speed, which is 2 pi r over the period or the time, first we must put the time in seconds. But you notice here that we weren't given the time. We were given how many revolutions it completes per minute. So the first thing I want to remind you of, and it's probably something you have had in the previous math class, and that is the period or time is equal to 1 over the frequency. In other words, what we have right here, 830 revolutions per minute, is actually the frequency. So when we put this in our equation, we have 1 over the frequency. And of course, now we have minutes per revolution. So minutes is my unit of time. And then of course, I can convert these minutes into seconds. So please review what I just said about what is given in this problem. What is given is not the time, but the frequency. And the time is 1 over the frequency. These are inverse properties. Please stop me at any time if you think I need to review something. So you notice here that this word revolution is not a unit. This word revolution just means how many cycles or how many complete turns it makes in a period of time. So the time, the minutes, is a unit, but revolutions is not a unit. Okay. So here the author wants to use the functions of a triangle, alpha, beta, and theta in a triangle of a unit circle or of a circle to show you how to understand the centripetal acceleration. So in the essence of time, I'm going to give you this equation because even though this is his derivation, what he basically wants you to know is that an object that is moving in a circle has centripetal acceleration, that is the ratio of the speed, the change in speed to the change in time. And the change in speed, he related to this triangle and its radius r. So when we compare this, we will see then that delta V by V, in other words, the change in delta V, and keep in mind from this picture here that the velocity we're talking about it's a change in velocity as the object goes in a circular path, like it did here. But now we've already said that this velocity, as we explained the definition, is constant. The object is traveling at constant speed, so the velocity is constant. However, the acceleration is a factor of the velocity and its radius. So now let me show you something else that I've given you in your notes. Okay, so here I highlighted in yellow the new equations that we're going to cover. So already we've talked about circular velocity, and we said that that velocity, V, is going to be the distance, which is 2 pi r, which is the circumference of a circle, divided by the period. The units are still meters per second. Now, this word centripetal means that this is the acceleration of an object that's moving in a circle as opposed to linearly. And this is defined as this velocity, whatever it is, squared divided by r. But the units are still meters per second squared. Okay. So for right now, I want you just to get a basic understanding of these equations. Okay. So now, the direction of the centripetal acceleration is towards the center of the circle. In other words, when you are solving for this centripetal acceleration, it is center seeking, which means that if we were to have, like in that first frame, an object moving in a circle, that centripetal acceleration is center seeking. Now, the question says, an object is in uniform circular motion. At point O, it is released from its circular path. Does the object move along the straight path between O and A, or along the circular arc between points O and P? And the answer is it moves along O and A, because once it's released, there's no longer a circular acceleration and the object moves off in a straight line. You probably have observed that if you ever put a rock or pedal on the end of a string and just swirled it around. That centripetal force is center seeking only as long as it is moving in that circle. Once you let go, it moves off in a straight line. Okay, the physics of a bobsled track. The bobsled track contains turns with radii 33 meters and 24 meters. Find the centripetal acceleration at each turn for a speed of 34 meters per second. So again, as always, these problems are solved by using the given. So in the first picture here, my radius is 33 meters. Okay. Find the centripetal acceleration at each turn for a speed of, so my speed is 34 meters per second. And we're trying to find acceleration. So of course, that's very easy to solve. A sub c, we know, is v squared over r. So we have 34 meters per second We square that, and we divide that by 33 meters. Okay, so our first answer we get, let's see, 34 squared, and we're going to divide that by 33. So we get 35. So the first answer we get meter squared divided by meter will leave me 1 meter per second square, and I have 35. So the first answer here is 35 meters per second square. Now let's do it here. What is my answer here? So here I have centripetal speed is 34 meters per second to be squared divided by 24 meters. And this time we get we get 48. Okay. 48 meters per second square. So this problem is a good problem to show you what happens. You see, the object is moving at constant speed. In other words, the speed is the same here and here. But what is changing is the acceleration. And we see that the smaller the acceleration, in other words, the smaller the radius here, the larger the acceleration. In other words, the same object has to accelerate at a higher rate because of the smaller radius. That's what you see here in this problem. So that gives you a good understanding as to what is happening. Even though I have constant speed, the acceleration varies depending on the radius. Then it says express answers as multiples of g. So in other words, how many g's is this? Well, we know that 1g is 9.8 meters per second square. So how many g's is this? Well, I divide this by 9.8 meters per second square. They'll tell me how many g's it is. Same thing here. Divide this by 9.8 meters per second square. They'll tell me how many g's it is. So when you hear them expressing something as a multiple of g, then you understand what that means. Okay, so in the first case, when the radius was 33 meters, the object is accelerating at 3.6 g's. And then when its acceleration, when the radius decreases, it accelerates at 4.9 g's. You can see the difference, what happens as the object is moving at the same speed, but different radii. Okay, if there are any questions, you feel free to come off mute and say, could you please explain that better or differently? And I'll be happy to do that. Okay, so recall Newton's second law. Newton's second law, we said, was the force is proportional to the acceleration and inversely proportional to the mass, or we wrote it linearly as F equals ma. So that means then the centripetal force of an object, we call that F sub c, is simply going to be the mass times the centripetal acceleration. So these little subscript c's tells us that this is the force of an object that's moving in a circle. Then, of course, now we know that we have another equation for A sub c, and of course that is V squared over R. So that's the equation for the centripetal force. So on your worksheet, here on your worksheet, centripetal force, you need to say that the centripetal force F sub C we know is mass times A sub C, which is mass times V squared over R. And of course, the units for force is newtons. That's the unit for force, newtons. Okay, so that's the equation I just gave you. So that can go on your notes. Now, the direction of the centripetal force always points toward the center of the circle and continually changes direction as the object moves. Okay, force is a vector, but it's continually changing its direction. Okay. The model airplane has a mass of 0.9 kilograms and moves at constant speed on a circle that is parallel to the ground. The path of the airplane and the guideline lie in the same horizontal plane because the weight of the plane is balanced by the lift generated by its wings. Find the tension. So we discussed tension in the last chapter, and this just another example that tension is a force. And in this case, the tension is the centripetal force. So in order to find the tension, I simply find the centripetal force. And my equation says mv squared over r, and now I'm able to solve that problem so easily. Okay. Now, before I move on to an unbanked, yes, ma'am?
Can you go back
Here,
to the one that we was just that one?
this one?
Yes, ma'am.
Okay. Tell me when.
Thank you.
Okay. So now I want to take you to the assignment that we have for this chapter. Let me see. Okay, so here we go. Let's work on some of these problems together. Again, the skill set that I want you to learn for all of these problems is how to begin. And of course, we always begin with what is given in the problem. So this problem says a ball moves with constant speed. So we're given the speed. Around a radius of 25 meters. What is the period? We're looking for t. Okay, so use your calculator to solve for t and show me which of these answers is t. No one has the answer?
Is it B?
I haven't solved it myself. Give me just 1 minute. Okay, I got 0.39. Okay, so I got 0.39. All right, let's see what someone said. Okay, Kaylin, very good. And then someone answered and said B. So that's good. So of course, in this problem, since we know our equation says V is 2 pi r over period. So this implies that the period is 2 pi r over V. So we're given R, we're given V, we can solve for T, which is a period. Okay, very good, Nigel. Okay, so that means that this very simple equation here, we can solve it easily. Okay, let's look at number 2. The second hand on a watch has a length. So if you're looking at a watch, you know that you have the second hand. So that represents the radius. The length here has the second hand on the watch. The hand is the radius. So that means that my radius is going to be 4.5. When I see the lowercase m, that means I'm going to do 10 to the minus 3 meters. And makes 1 revolution in 60 seconds. So my period then is 60 seconds. What is the speed of the end of the second hand? So what's the speed at the end of the second, at the end? So of course, we're going to solve this equation. So we're going to put in 2 pi times 4.5 divided by the period. What do we get? Let's do that one together. Okay. So when we put it in our calculator and solve for it, we get 0.471 times 10 to the minus 3, and this will be meters per second. But they want us to write it in scientific notation. So therefore, this number has to get larger. I multiply this by 10. I multiply this by a 10th. So this gets larger by factor of 10, and this gets smaller by a factor of 10, which means I multiply it by 10 to the minus 1, and therefore this is my answer. Okay? Any questions on that problem? Okay. Let's look at number 3. Okay, number 3. Now this problem, I want to show you a couple of ways to make the problem easier to solve. And this is what I mean when I say learning good problem solving techniques. So it says approximately 1 billion years ago, the moon orbited the Earth much closer than it does today. The radius of the orbit was only, okay, so now we have to find a way to distinguish these numbers. In other words, it says we're comparing, well, let's finish reading the question. The orbital period was this. Today, the average radius is 385,000 kilometers, and the present period is this. Assuming that the orbit of the Earth is circular, calculate the ratio of the speed of the moon and in its ancient orbit to the speed that it has today. So they say calculate the speed, and we'll say at ancient times to the speed it has today. It says calculate the ratio of the speed of the moon in its ancient orbit to the speed that it has today. So let's see I have a question. Hold on. The answer to number 2 was D. Yes. Okay, the answer to number 2 was D. Okay, so here we need to find the velocity ancient. That means we need to have 2 pi r at ancient times divided by the period at ancient times, and that's divided by 2 pi radius today divided by the period today. But you notice here very quickly that 2 pi and 2 pi cancels. And to solve this problem, we are going to divide by a fraction, and we said in the denominator of the denominator moves to the numerator, which means then that we're going to have the ancient radius divided by today's, the ancient period, and then this moves to the numerator. So we're going to have today's period, and we have in the denominator today's radius. So that's what we need to solve. So let's go over here now and write these numbers down. The radius of the orbit was only, so that's the radius ancient. And ancient, it was 2,4,4,0,0 kilometers. The orbital period, it means the period ancient was 2,3,4,0,0 seconds. Today, the average radius is, so today, the radius is 3,850,0 kilometers. And the present period, this is not the right subscript. Hold on one second. Okay. Today, the average radius, this is today. And the present period, that means today's period, is 2.36 times 10 to the 6 meters. Now, I believe that the author gave us this last number in scientific notation as a clue to the best practice in writing these numbers down. So that means that over here, we should say 2.44, this is a decimal, 2.44 times 10, and this will be 1, 2, 3, 4, fourth kilometers. Right here, we should say 2.36 times 10, 1, 2, 3, 4, fourth seconds. Right here, we should say 3.85 times 10, 1, 2, 3, 4, 5 kilometers. And the reason why we want to do that is because we're going to see that using the exponential form, writing these numbers in scientific notation, actually makes the number a lot easier to manipulate. So now we have, so we're going to solve the radius at ancient times the period today divided by the period at ancient times and the radius today from here. So now let's plug these in. So we have 2.44 times 10 to the 4th kilometers. T here, 2.36 times 10 to the 6th meters. TA, we have, oh, this is supposed to be a 4 right here. I'll find it, I'm the same. We have 2.34 times 10 to the 4th seconds. And we have RT, which is here, 3.85 times 10 to the 5th. And this is kilometers. So you notice I didn't do anything to the units because a ratio, we know the units will have to, oh, what I have wrong right here, class, this is what? This is seconds, T sub T, that's seconds. That cancels that one, okay? All right. Now, right here, what happens? 10 to the 4th, 10 to the 4th cancels. 10 to the 5th, that means that this will cancel all of these but one, just leave me 110. So now my calculator is so easy. 2.44 times 2.36 times 10, divide 2.34, divide 3.85. So what do we get? Let's do that together. Okay, so let's see what you all got. Give me your answer in chat for this problem right here. Very simple problem. Okay, anyone can give me the answer in chat? We're just multiplying these numbers here. Just a simple multiplication in your calculator. Okay. Okay, Lanisha, look at where your decimal is. Okay. All right, the answer is E. I want Lanisha, look at yours again and see where your decimal is. I think maybe you left off this 10 right here. Okay. We have a guest today. I invited someone to sit in on our class, and Yannick is here today, so he sees, he's also just auditing the class today. Okay. Okay, I see some of the answers are good, so that means that I think that you all are understanding. Just a matter of multiplying these numbers and then dividing these numbers. You just can't go wrong if you do that in your calculator. You should get E. Okay. Let's move along now to number 4. Let me see. Okay, number 4. A solar-powered car is traveling at constant speed around a circular track. What happens to the centripetal acceleration of the car if the speed is doubled? So we know that centripetal acceleration is v squared over r. And the question is, what happens to the centripetal acceleration of the car if the speed is doubled? So that means that when I double the speed, rather than having v, I have 2v. So 2v has to be squared over r. So when I square that, of course, I get 4v squared over r. So that means then that the centripetal acceleration compared to this one is 4 times greater. So we say the centripetal acceleration increases by a factor of 4. So that's why you have to plug it in carefully to see that these square. Now, let's look at number 6. Because this is actually your homework. I don't want to do them all, but I want you to see if you understand how to do what is meant by this equation. So let's look at number 6. Okay. So you work on that one. Let me see if you understand how that equation is understood. Okay, I'm looking for you to work on number 6 and then put your answer in. Okay, I have an answer. Let's see what someone has said. Okay, got one answer. Okay. All right. So my answers are: the centripetal acceleration remains the same. The centripetal acceleration increases by a factor of 3. The centripetal acceleration increases by a factor of 9, decreases by a factor of 3, or decreases by a factor of 9. So let's look at the problem and see what's going on. We know that my equation says that, let's see, I have another choice. Let me see what somebody's saying. Okay. All right. Let's just look at this problem together. So it says that the centripetal, we defined it A sub c as v squared over r. Now it says if the radius of the circle is reduced to r, let's just put a capital R, to r by 3, while the period remains the same, what happens to the centripetal acceleration of the rock? So that means that we have the same period, but R is reducing. So since they introduced the period, let us go back now and look at what happens to the speed when, well, it says the period remains the same. So V remains the same. Okay, so that doesn't change it. So let's look at this then. A sub C, we know is V squared over R, but now R is reduced to R by 3. Okay, but in the denominator of the denominator, we know that that term moves to the numerator. So we have 3V squared over R. So that means then if I compare this to this, that my acceleration has increased threefold, 3 times the original number. And remember, we said early on, back in our notes, what happens to the acceleration when the radius is reduced. So we know that it has to increase. We saw that. Let me just show you again. So I want you to see that picture. Hold on. Okay. Right here. Okay. We said, what happens when the radius is reduced? And we said when the radius is reduced, that the centripetal acceleration has to increase by some factor. So that's one thing you want to keep in mind. As keeping the period constant, if we reduce the radius, the acceleration has to increase. That's what that problem is asking you to think about. So that the first thing you know is it has to increase. So that kind of narrows your choices right there. Okay, let me go back to the question. Oops. Hold on, let me get this. I don't know why it's not sharing. Hold on. Okay. Okay. All right. Let me trying to clear all drawings, and I'm trying to get back to the problem, but for some reason it's not letting me do that. Let me see. What do you all see right now? Do you all see 5.2?
No, I see the homework problems too.
Oh, but I don't see that though. Hold on. I don't see what you see. Give me a minute. Hold on, I'm stuck. Let me stop sharing. Okay. Let me try again. Okay. All right. Now, okay, so our answer would be increases by a factor of 3. So the main thing you want to be able to know is that it has to increase. It can't remain the same, and it can't decrease. So it increases by a factor of 3. All right, let's go to number 7. Well, that's an easy one. I'll leave that one for you to do. That's an easy one. Let's go to number 8. Okay, number 8. A satellite is placed in a circular orbit to observe the surface of Mars from an altitude of 144 kilometers. The equatorial radius of Mars is 3,397 kilometers. If the speed of the satellite is given, what is the magnitude of the centripetal acceleration of the satellite? I want you to be very, very careful and write down what is given in the problem, what's given in the problem, what equation you're going to use, and then solve for the centripetal acceleration. Okay, I want you to work on that one so I can see if I need to further explain that equation. Okay, so let's see. Okay. Does anyone have the answer yet? So all we're doing, class, in this problem, and I don't know what um, I saw that two people, Nigel, okay, Nigel and Yannick have the problem, but I'm seeing why the others aren't answering it correctly. All right, so in this problem, class, all you're doing is you have to know if you're going to solve v squared over r. V is given, but what is r? In this case, it says that the satellite is placed in a circular orbit to observe the surface of Mars from an altitude of this. So that means that the r that I'm looking for has to be the radius of Mars plus the height above Mars, and that is kilometers. Okay, so that would give us then, and we want this is given in meters per second. So we have to say, okay, this means kilometers. So that means I have this number times 10 to the third meters. And then when I solve the problem, I should get 3.42 times 10, meters per second squared when you solve this problem. So just take it, just very, very methodically put in your calculator. You just can't go wrong if you take your time. And just remember, kilometers needs to be 10 to the third. Okay. So I will leave some of these for you to do for the homework assignment. Let me see. Okay. Don't forget that if you're given the time in minutes, you need to convert that into seconds because all of our units are in seconds. So it takes 1 minute to complete revolution. You know that means how many seconds? Okay. Let's look at one like number 13. A certain string just breaks when it's under 25 newtons of tension. So that means then that this tension, okay, he's whirling in a circle. So this tension is what's providing my centripetal force. So my centripetal force of my tension is 25 newtons. A boy uses this string to whirl a 0.75 kilogram stone. So my mass is 0.75 kilograms. Okay. My radius is 2 meters. The boy continuously increases the speed of the stone. At approximately what speed will the string break? So he wants to know at what speed V will the string break. So now what equation am I going to use? I have to use the equation that relates centripetal force to speed. And of course, that equation we had said that my centripetal force is mv squared over r. So here, v is my only unknown. I know m, I know r, I know f sub c, I can solve for v. So this implies that v equals what? So please solve for v. From this, given these values, this number, solve for v. And what do you get? Okay, no one has the answer yet? Okay, we're solving number 13 and we're solving for V. Okay, let's see what somebody's saying. Okay, I have one choice, all right. Okay, I see a couple of answers. Okay, now in this problem, what you're gonna have to remember is that V is squared here in the equation. So that means your answer, of course, is going to be the square root. The square root of what? We're looking for V, so multiply R on both sides. So we're gonna get F sub C times R, and then we're going to divide by M. And whatever the answer is, we're going to get the square root of that answer. So make sure that you are solving it correctly. Okay. Make sure so now do we have someone who can't get the answer? The answer, when I solved it, I got 8.16. Okay. I got 8.16. Of course, the units are meters per second. That's the answer you will get in your calculator. But of course, when you come up here to choose the answers, the closest answer, of course, is B. Okay, very good, Nigel. Okay, very good. All right, so I'm just making sure in this exercise that you all understand these very basic equations. So once you understand that, then I'm ready to move on to the next section. So we've solved quite a few of those. So you only have to do a few more of these in the homework, and you can see that most of these now are concept questions. These are concept questions. Now, number 20, you won't be able to solve until I go over this next part. So now I'm going to go over and talk about number 20. I mean, how to solve number 20. So let me go back to my my lecture, okay? So here, we're talking about the centripetal force on an unbanked curve. By an unbanked curve, what we mean is the surface is level. There is no angle. Everything is is horizontally level. So on an unbanked curve, the static frictional force provides the centripetal force. In other words, the static frictional force between the tires and the surface, the static frictional force is providing the centripetal force. That's on an unbanked curve. Now, on a frictionless banked curve, the centripetal force is the horizontal component of the normal force. Now remember, we've gone through and I've shown you how the normal force is always the perpendicular component, okay? But the weight is always acting straight down. So when it says on a frictionless bank curve, the centripetal force is the horizontal component of the normal force. So this normal force now, F sub n, has a horizontal component and it has a vertical component. And the vertical component of the normal force balances the car's weight. So you can see this. We went over this in the previous chapter. So now we have the two equations. What the author does then, he says, okay, in a banked curve, we have the centripetal force here that is F sub n sine of theta, and that's equal to this equation of the centripetal force, and the car's weight is balanced by this vertical component. This is on a banked curve. So what he's done now is given us an equation by dividing this. See, this is just dividing. So F of n and F of n cancels out. This m and this m cancels out. V squared over RG, it remains. And of course, you know that sine theta divided cosine theta is tangent theta. And therefore, we have an equation that we can find the angle of a banked curve. The important thing I want you to notice in this equation that is we have eliminated the mass. So that means that when you engineers and those of you who will be doing civil engineering, road construction and all that, there is an angle theta. Okay, there's an angle theta whose tangent is the velocity squared divided by RG. Now, what do you notice here? You notice here that for any angle theta, there's a fixed speed that is just related to the radius. So that means that when you're driving, say you're driving you're coming off 565, you're coming onto North Parkway at University, and it gives you a speed, a minimum speed. That minimum speed now has been chosen for a lightweight car, for a big 18-wheeler, for a heavy truck, for a light van. All of that is because that angle theta of that bank curve is already chosen based on the maximum speed that one should be navigating that curve. So that's called the angle of bank curve. So also in your notes, if you will look, let's go to here. Okay, angle of bank curve. That equation goes right there. And if you put it in as angle, like theta equals, of course, the unit will be in degrees. Okay, so now here, everything we have before that is what you've already learned. To some degree, you've already learned this. So I just highlighted what we're doing that's new. So far we've covered all of this. We only have 2 more equations to cover in this chapter. Okay, let's do that kind of quickly. Okay. Okay, so let's move on. Let's see. Why it doesn't want to move on? Hold on. Okay. Okay, so you can solve that problem. It's a pretty easy problem to solve. All right, now this is important. There is only one speed that a satellite can have if the satellite is to remain in an orbit with a fixed radius. So remember last time we discussed that between any 2 objects, there is a gravitational force. And now we know that in addition to that being a gravitational force, if the object is in an orbit around another object, that same object, there's also a centripetal force. So here what we have done is we have equated the centripetal force to the gravitational force. Okay, and the gravitational force, this is the equation. The centripetal force, this is the equation. So what you notice then is that these m's cancel. Okay, this r cancels one of these r's. So now we have v squared is big G, mass of Earth, divided by r. Or to get v, take the square root of that. And that's where this equation comes from. So what does that mean? Just like our moon is a natural satellite. The moon is orbiting the Earth with a given radius. Of course, we know it fluctuates, but we're going to just, for our practical purposes or for calculation purposes, we're going to assume it's a radius, a fixed radius. So that means that any other satellite that we put out in the Earth's atmosphere here, that speed is fixed, and it is a factor of the inverse of the square of the radius. That's what it means. That's why when you read about space junk, you will understand that the stuff that's out there, communication satellites and all these other satellites, they're out there and they're orbiting the Earth, and they remain in Earth's orbit. Even when they're no longer functioning, they still can remain in Earth's orbit, moving at this speed. Okay. Then lastly, we have one last equation, and that equation is the period of a satellite. So now all the author has done here is to find the period of satellite when the speed is not known. We simply have to put in the equation for speed, which is 2 pi r over t, and now we're going to solve for this t. Now this is a good derivation for you to practice. In fact, I want you tonight to just make sure you understand how to do these algebraic manipulation to solve for this t. If you can do that, that will prepare you for some of the next questions that are coming up in that assignment. Okay, so satellites in circular orbits is what we use to for the GPS system. So now you've learned a little bit about how we're able to use physics in our real world to give you real-time data. And it's amazing how if you say if you're traveling on the interstate, it's amazing how it can update so quickly to tell you how much time you would need to reach a certain destination, or it can tell you minute by minute where to turn. If you put in that address, you're trying to find Alabama A&M as you are approaching, say, the Parkway off the interstate, it'll tell you to exit, make the next exit, and so many feet you're going to merge onto North Parkway. I mean, all that is just so precise, and I find it quite amazing that using this equation, of course, a more I would say high order of this equation, we're able to solve and use all of this data in the GPS positioning system. Okay, so we're going to stop there. That's basically what we have in this chapter. So I've covered this chapter. We're going to spend tomorrow going over the exam. Please look in your notes for the midterm. The midterm will cover chapters. So I'm going to grade the exam first and use the answers that I have on the exam to choose some of the questions that you have done well in, as well as a couple that I want you to work a little harder on. So I'm going to make the exam sort of maybe 60-40. 60% will be the material we've already covered in chapters 1, 2, and 3, and 40% will be some questions from chapter 4. And I need to get this back because I just remembered I've got to post these midterm grades. So that's why I really need to go ahead and get your a midterm exam. Okay, hope I haven't gone over much. Let me just can I call you right back up? I'm still in class. Can I call you right back in 1 minute? Okay. Okay, class. So, so here you have your equation quiz. Put all your equations there. Then you have your homework. Finish that homework. If you don't finish that homework, I would say if I have to give priority, I will give it to the midterm. Of course, I haven't sent the midterm out yet, so you still have a chance to. You have time to work on this before the midterm comes. Please let me know if you need more time on the midterm before you want to submit it. It shouldn't take you more time because I'm going to pull the questions from the previous assignment, and then I'm going to add 40% from chapter 4. So that should give you a good chance to get a good grade on the midterm. Okay, so we'll end there. If you have any questions, you can put them in chat now or send me an email. Otherwise, you can sign out and I will see you all tomorrow.